Now, when we're looking at this, if we're in a production facility and we are manufacturing soccer balls, baseballs, I don't know. Any baseballs? All right. So we have certain standards that those baseballs have to meet to be acceptable. So we're not going to test every single baseball that comes off the line. We're going to pull some, and we're going to use those as our sample. And we'll look at our sample means. Of the ones we pulled, let's say 10,000 come off the line in the day, we pull 100. And we'll test them for quality purposes. So we might weigh them, we might find the circumference, different things that we would do with these baseballs that come down the line. So that data is what we could do to find a confidence interval. So with our confidence interval, we're going to take the sample means. So we'll take the mean of the sample. Now, what symbol denotes a sample mean?
The E. The E looks like X. Gotta be the E.
Okay, that's standard deviation of a sample in the calculator. We have two that need mean. This one and this one. Which one's for a sample?
Yes.
Yes. Okay, X bar. Plus or minus what we deem our acceptable margin of error. Okay, now this is the formula to find the margin of error. It is Z star. And Z star represents the Z-score associated with the confidence interval. And I'll show you how to find that in just a second. That's not supposed to make sense yet. Times the standard deviation of the population divided by the square root of n. Now, when we take the standard deviation of the population and we divide it by the square root of n, this actually gives us the standard deviation of a sample.
Is that divided by the square root of the standard deviation?
Yes, the standard deviation of the population, I think these kind of ran into each other, divided by the square root of n. And n represents the number in the sample. Yes, ma'am?
Is Z-score associated with what?
The confidence interval. Okay. So, if we wanted a 90% confidence interval, as a production manager, I would not be happy with a 90% confidence interval. I would want it to be a good bit higher. But let's say we wanted a 90% confidence interval. What does that mean? If I look at my data, and a confidence interval is going to give that range in which the true mean of the population will fall. So the mean of our data is in the middle, right?
Yeah.
But we want to be 90% confident. So if we know we want the mean in here somewhere, we want this middle part to be 0.90. So we can have that 90% confidence. Now, that gives us this middle part from here to here. So what does it leave in our tails? Yeah, 5% on this end and 5% on that end. Because it leaves 10%, and 10 divided by 2 is 5. It leaves 5% over here, or 0.05, and 5% over here. Now, that Z star is this upper bound. It's that upper bound of your confidence interval. So if we wanted 0.90, this upper bound is the 0.90 plus this tail. So it would be associated with a 0.95. Okay, now I like to draw the picture because I'm visual. So to find Z star for me, it's very helpful to just draw the picture. You may be a formula person. So to find Z star, it might be helpful for you to know that every time it's that confidence level plus 1 minus that confidence level divided by 2. Every time that's what's going to happen. So in our case, it was 0.90 plus 1 minus 0.90 divided by 2. Isn't that how we got a 0.95? So some of you might like a formula. There's the formula. I like the picture. I like to draw it. Okay, now, this kind of takes us back to last night's homework. We want the probability to be 0.95, so let's go back. 0.95. Do we see that 0.95 is exactly halfway in between these two? So what Z-score goes with that? I'm going to come out this way, and I get the 1.6. I'm going to go up here, and it's halfway in between these two. So the Z-score that goes with a 0.95, that Z-score is 1.645. Because it's halfway in between these two, isn't it? So it's halfway in between the 4 and the 5. So this Z-score is 1.645. Okay, let's see how it works in a real problem. Are you starting from the beginning, or are you just writing this last little part?
I'm done.
Okay. All right, so in this example, a college admissions director wishes to estimate the mean age of all students currently enrolled. So this is what we're looking for, the mean age of all students. In a random sample of 20 students, the mean age of the sample was 22.9 years. That's kind of older for a college, isn't it? From past studies, the standard deviation is 1.5 years. So we know that our sample size is 20. We know that the mean of the sample is 22.9. We know that from past studies that the standard deviation of the population is 1.5. Now, we have to find the Z-star for a confidence interval of 95%. That's what we're missing. We've got everything else we need in the formula except this. So let's start there. If we want this region to be 0.95 so that the mean falls in there, that leaves 5% for both tails. So each tail would be 2.5. So this was 2.5%, which is 0.025. So what would this upper bound be? 0.975. When we add these two together, we get this upper bound. Okay, so now let's start. My confidence interval is equal to X bar, which is 22.9, plus or minus a Z star that goes with a probability of 0.975 times my standard deviation divided by the square root of n, which is 20. All right, let's go to our chart and see if we can find the z-score associated with a probability of 0.975. So 0.975. Oh, it's perfect.
Can you go over how you got 0.975 again?
Sure.
Sorry.
Let me steal this while I'm here. 0.975 is right here. So this is 1.90, 1, 2, 3, 4, 5, 6. So this is 1.96 that I'm looking for. Okay. So if the confidence interval is 95%, that means the middle part has to make up 0.95, which leaves 5% for both tails. So this tail is 2.5%, this tail is 2.5%. Z star represents this upper bound. So to get the upper bound, it's this plus this.
That's
Okay? So, and we just discovered that this Z star is 1.96. So now, guys, you need to do this calculation. 1.96 times 15 divided by the square root of 20.
15 or 1.5?
That should be 1.5. Thank you. That is 1.5. I missed the decimal. That would make a huge difference.
Why is it 1.966?
Oh, that is the z-score that's associated with a probability of 0.975. Remember just a second ago we found the 0.975 and that z-score was 1.96.
Oh, so you go, okay, never mind.
Okay.
I see what you did.
So this is 22
So this z
plus
score,
or minus.
so this z score and the chart.
Did you guys get 0.66?
Sure.
All right. So this is going to give us that range. So we subtract. And we get the lower bound. We add, guys, you need to hush so you don't get thrown out, the upper bound. Okay. So this is our interval. That's it. We want, the age, we are 90% confident, not 90, 95% confident that the age falls within this interval. And that's how we say it. This is a fill in the blank. We are blank percent confident that the true mean and then here we have to say what the problem's about. That's not a line, that's a wave. Is between, this is statistics. So all of you that are signed up for statistics, this is statistics. Blank and blank. Okay, so for this problem, my confidence level was 95. Plug it in. We are 95% confident that the true mean what? This one's about the age of all students. Is between my lower bound, 22.24, and my upper bound, 23.56 years of age. Define my unit.
It's not like hard, it's just like a lot of
Yeah. That's why I wanted multiple days to practice instead of just having one review day.
Oh, that is.
We need practice days. All right, now, example 2 has to do with soccer balls. But it says, a manufacturer wants to estimate the mean circumference of the balls within 1.1/10 of an inch. That 1/10 of an inch is what that manufacturer will accept. If it's off by 1/10 of an inch, I'm good with that. That is margin of error. That's what they're okay with. So, this problem isn't about the whole confidence interval. This is just about the margin of error part. So we know that the margin of error is that second part. So margin of error is equal to z star times sigma divided by the square root of n. Alright, it tells us this acceptable margin of error is 1/10 of an inch. We can plug that in. They told us. We know. They give us the population standard deviation, 0.25. We can plug it in. Determine the number of balls. We are solving for n. N is what we don't know. How many balls do we need to sample so that we can be 99% confident? So we want a z star that corresponds to a probability of 0.99. Now, 99% confidence. 0.99 confidence. All right, what is the probability that gives us that 99% confidence interval? Let's look at it. It's this upper end. So if this is 0.99, there's 1% left. What is 1% divided by 2? 0.5%. 0.5% over here, 0.5% over here. So this is 0.995. The probability for 99% confidence is 0.995. Look up the z-score for a 0.995. You're about to see there's a bunch of them. 0.995, 0.99. Oh, okay, it's halfway in between these two. So it's 2.575. Yeah, it's 2.575. So this becomes 2.575. And then we just have to do a little algebra. Not hard algebra, simple. We want to solve for n, so we got to get it out of the denominator. And then we would have to divide by 0.1. So the square root of n is equal to 2.575 times 0.25 divided by 0.1. And then you square both sides. All right, punch that in, see what you get. $41.5 something? Let's see. 45? Okay.
No, I got 41.
All right, 41.441 balls. Can we actually test 41.44 balls? How many balls do we need to test? 42 balls. If we tested less than that, we would not be 99% confident. We would be less than 99% confident. But if we test 42 balls, then we can be 99% confident. Okay, so what you picked up as you came in was some practice with confidence intervals and margin of error. All right, I would like you to finish the front before the bell rings.